Next, we're going to be taking a look at another example. So in this example, we'll be exploring the density of water as a function of the temperature. And we'll be using SI units, so density will be recorded in kilograms per cubic meter, and the temperature will be recorded in degrees Celsius. So I have two data points that give the temperature of the water and the corresponding density. So at 50 degrees Celsius, the density of water is 988.1 kilograms per cubic meter, and at 60 degrees Celsius, the density of water is 983.2 kilograms per cubic meter. So what we're going to be doing with this is we're going to be describing the density as a function of the temperature, and then we'll proceed to construct the entire derivative and inverses map, so the whole D&I map. So we'll look at, for example, f of 50, f prime of 50, f inverse of 988.1, and f inverse prime of 988.1, approximating those things using this table. So to begin, let's first start by just defining our function. So let's let rho equal f of t. So here we're saying that the density is a function of temperature, and this functional relationship is given by the function f. So when we differentiate this, we get d rho dt is equal to f prime of t. So that's the derivative of this function f with respect to time, and that measures the rate at which the density is changing per change in degrees Celsius, in other words, per change in temperature. Now, if we look at the inverse of this function, we obtain t is equal to f inverse of rho, and then differentiating the inverse function, we get dt d rho is equal to f inverse prime of rho. Now remember, this prime is acting on the function f inverse. So f inverse itself is just a function. It's no different than the function f, it just has the name f inverse. So f inverse is a function, and since like any other function we can differentiate it, so the derivative will be f inverse prime. And so since f inverse takes rho as an input and returns t as an output, the derivative of f inverse will give a differential change in t divided by a differential change in rho. So it's the rate of change of temperature per change in density. So that's what f inverse prime measures. Now if you take the inverse function of f prime, so we already said that f prime was d rho dt. So if we do the inverse, apply the inverse function to this, we get something different. We get t is equal to f prime inverse acting on d rho dt. So you can see again the order matters whether you say f prime inverse or f inverse prime. F inverse prime is the derivative of the function f inverse, so it gives you dt d rho. F prime inverse is the inverse function of the derivative, so it tells you the temperature as a function of the rate of change of density with respect to temperature. In other words, the temperature as a function of d rho dt. So you can see that you want to always pay attention to whether it's f inverse prime or f prime inverse. Those give two different things. Now we just have a table of data, and so we can use these data points to approximate different values of each of these five main characters in the D&I maps. So this would be the derivative and inverse maps for our function, the density as a function of temperature. So to start, we can do the easiest one, and that is the first one. So we'll take a look at this. So first, let's say, well, this is simple. If we evaluate f at 50, we can write f of 50 is equal to 988.1. Right, because we can literally just read this off of the table, right? So at 50 degrees Celsius, the density of seawater is 988.1 kilograms per cubic meter. So, and that's pretty much the physical interpretation of this. So the physical interpretation is, So we can say when the temperature of the water is 50 degrees Celsius, then its density is 988.1 kilograms per cubic meter. Right, so the input is 50 degrees Celsius and the output is 988.1 kilograms per cubic meter. Now this is going to give the exact same information as F inverse of 988.1 is equal to 50. Right, so that's how the inverse function works. Instead of taking the input and assigning the unique output, it looks for the output and says, okay, what input value led to that output? So in this case, 50 degrees Celsius was the input value of the function f that returned an output of 988.1 kilograms per cubic meter. So the inverse function literally just switches the roles of the x and y variables, or in this case, the rho and the t variable. So here we can say when the density is 988.1 kilograms per cubic meter, then the temperature is 50 degrees Celsius. Right, so it's an equivalent statement. It's the same information in both of these statements. Just, to mirror the functional notation as closely as possible, I like to start with the input. So I always like to, when doing these interpretations, start by the input, because whether you have f or f inverse, they're slightly different statements, right? So f of 50 equals 988.1 says, what is the density when the temperature is 50 degrees? Whereas f inverse of 988.1 equals 50 says something different. It says, well, what's the temperature when the density is 988.1? So the two, go hand in hand, because 50 belongs to 988.1 and vice versa. So I always like to start off my sentence when I do a physical interpretation with the input, because I'm saying, okay, well, the first in case we have when the temperature is 50 degrees, then the density is equal to this, 988.1. In the second case, we're saying, well, what's the temperature, when the density is 988.1, what is the temperature? So we're starting with the density and saying, well, what's the corresponding temperature? So I like to let that fact reflect in the wording when I interpret this physically. Otherwise, there's really, the data point is exactly the same. So okay, so now let's go on to the next one. So let's start doing derivatives. Okay, so for the derivative, so d rho dt, this is going to equal f prime of t. So that's just straight from the derivative and inverses map that I had set up. So now we're looking at, well, what's the change in density with respect to temperature at a certain temperature? So we want to say something like this. F prime of 50 is equal to something. And we don't have an exact value, but we can approximate it using the information from the table. So this is really, recall that the definition of the derivative, d rho dt, or f prime of t, this is going to be the limit as h goes to 0 of f of t plus h minus f of t over h. Now when we look at this, the top basically tells us a change in density, right, delta rho. And h is the change in temperature, because we're evaluating this function at t, so at one temperature, t, then we're evaluating it a second time at t plus h. So h is the change in temperature, so this h down here represents the delta T. So therefore, to approximate the derivative, which is this ratio in the limit as delta T goes to 0, to approximate that limit, we can just, say it's approximately delta rho delta T if delta T is small enough and if rho is changing slowly enough over that interval for this approximation to be valid. So the best we can do is take delta rho, so 983.2 minus 988.1, and then divide it by the corresponding delta T. So we're dividing by 60 minus 50. And this gives us exactly minus 0.49. So f prime of 50 is negative 0.49. Okay, so now let's interpret this in words. So here we're saying, and of course we always want to refer to our derivative and inverses map. So negative 0.49 gives an approximate change in the density for a single unit increase in temperature. So we can say, start off by saying, when the temperature of the water is 50 degrees Celsius, basically an increase of temperature by 1 degree Celsius will result in a corresponding decrease in density by approximately 0.49 kilograms per meter cubed. So a couple points on how I constructed this sentence. So first of all, I started off by saying, with the input. So when the temperature is 50 degrees Celsius, right? So I'm looking at the input of this function. So when the temperature is 50 degrees Celsius, now I have to say what the minus 0.49 represents. So the output of this is d rho dt. So it's a change in density per unit increase in temperature. So a few things I should point out. So when I didn't say for every increase of temperature by 1 degree Celsius, I never say for every, because that means that the next increase will be the same change in density. So for every degree you increase it, you always get a 0.49 kilogram per cubic meter drop in density. This is true only in the limit as the change in temperature goes to 0. So by saying, for every increase in the temperature by 1 degree, you get this change in density is inaccurate, because that would imply that the function is linear, right? Because you're saying no matter how many increases in the temperature I take, it's still going to change. The density will always change at this rate. But the rate of change of density with respect to temperature is not, it's always changing. So if I were to look at d rho dt at 51 degrees, it would be slightly different than d rho dt at 50 degrees. Now you can't see that here because we're just approximating d rho dt using a 10-degree interval and using these data points. But if you had the exact values for d rho dt, it's not a constant, right? So d rho dt is gradually changing with the temperature. So at 60, d rho dt might be different than it is at 50, and it's going to be different than it is at 51, and it's going to be different than it is at 51.2. So we just want to say, if we increase the temperature by 1 degree Celsius, and that's just a small change in temperature, and it's small relative to how quickly the output is changing. So even in a 10-degree change in temperature, we didn't see a big change in the output, right? 983 versus 988, it's less than a 1% change. So 1 degree change in temperature, we're looking at a very small change in the density. So we can say an increase of temperature by 1 degree Celsius will result in a corresponding decrease in density by approximately 0.49. So I want to say approximately, even if f prime of 50 is exactly equal to minus 0.49, in other words, even if this was an exact value that we obtained, we still want to say that it results in approximately a decrease of 0.49 kilograms per cubic meter, because it's only exact in the limit as the change in temperature goes to 0. So technically, even if the change in temperature was only 0.00001, the corresponding change in density, cannot be exactly measured using the derivative, right? It's just in the limit as the delta t goes to 0. So it's always an approximation. So it's basically, a manifestation of saying delta y is approximately f prime of x times your delta x. No matter how small you make delta x and delta y, it's still an approximation, right? Only in the limit as delta x goes to 0 does this become an equality. So this approximation approaches an exact equality in the limit as your interval becomes infinitely small. So we always want to state the word approximately. And then instead of saying will result in an increase of negative 0.49, nobody talks like that, right? So if you want to hear, hey, we have a negative increase today. They say it decreases, right? So I want to convert this minus sign into something that people will understand more practically. Okay, the density is going down by approximately 0.49 kilograms per cubic meter. So even if somebody who doesn't have any experience with calculus, they don't know what f prime of 50 is equal to minus 0.49 means, but you can still say, okay, when the temperature of the seawater is 50 degrees Celsius, at that point, then see how it's natural to say then every increase? No. Then if the temperature were to increase by an additional degree, so if the temperature were to become 1 degree warmer, then the density would decrease by approximately 0.49 kilograms per cubic meter. Right? It makes sense saying it like that. Right? So we did these ones. So now let's do this one. So that one we had. So this is a little bit different because it's f inverse prime. So we had previously f inverse of 988.1 is equal to 50. And this is going to be f inverse prime. So first of all, it's f inverse prime of rho. So it's f inverse prime of rho. So that means it's going to be f inverse prime So it's f inverse prime. Rho is 988.1. Now this does the opposite of what just f prime by itself did. F prime measured the change in density with respect to the change of temperature, whereas f inverse prime measures the change in temperature with respect to a change in density. So instead of using delta rho over delta t, I use delta t over delta rho. And that results in just the inverse, so minus 2.04082. So this is approximately 1 over negative 0.49, right? Because if this one is a change in density divided by change in temperature, this one's change in temperature divided by change in density, those two are just the reciprocals of each other. And we'll explore that in greater detail in section 3.8. But for now, we can just take the reciprocals. But of course, f inverse prime is not evaluated at 50 degrees, it's evaluated at rho. It's evaluated at 988.1. So the physical interpretation of this is when the density of the water is 988.1 kilograms per cubic meter, an increase of 1 kilogram per cubic meter in density will result in a decrease in the temperature by approximately 2.04082 degrees Celsius. So in other words, when the density is at 988.1 kilograms per cubic meter, if the density were to increase by 1 kilogram per cubic meter, then the temperature will decrease by approximately 2.04082 degrees Celsius. Right? So it's per unit increase in density, so per delta rho, the delta T is -2 approximately, -2.04082. So a 1 degree increase, or 1 kilogram per cubic meter increase in density will result in a corresponding decrease in the temperature by approximately 2 degrees. So again, instead of saying increasing by -2, I'm translating that into English by saying it decreases by 2. Right? So a decrease by 2 is the same as an increase by -2, but to make it, interpret this practically, you say a decrease by 2. And also, if you are ever given the other way around, so if you're ever given a problem where it describes in practical terms a mathematical statement and then it asks you, okay, well, write the mathematical statement that this corresponds to, always pay attention to whether it says increase or decrease, because that will key you to the sign of the derivative if you're talking about a derivative. And then f prime inverse, so this is a little bit more advanced than the other four because we are taking the inverse function of the derivative. Well, actually, it's not too bad because I kept this statement alive up here. F prime of 50 is -0.49. So the inverse function just switches roles. So from that, we can say f prime inverse of -0.49 is equal to 50. And let's describe how to explain that statement in practical terms, because that's another interesting one. So for this one, we can say, so here we're starting with the derivative, so that's a little bit different than the other one. So we can say, right, because this one represents d rho dt. So when the density decreases by 0.49 kilograms per cubic meter by approximately, always say approximately, when the density decreases by approximately 0.49 kilograms per cubic meter, let's say pursuant to a 1 degree Celsius increase in the temperature, then the temperature is 50 degrees Celsius. So it's basically saying when you're at the point that a 1 degree increase in temperature results in approximately a 0.49 kilogram per cubic meter decrease in density, then your temperature is 50 degrees. So it's starting with the derivative saying when the derivative has this value, this is what the temperature is going to be. So that's another example for these D&I maps. And basically it's just getting a handle on understanding this notation. When you see something like, f prime inverse of -0.49 equals 50, what on earth does that mean? Well, you can construct it kind of piece by piece when you construct these D&I maps to help guide you into saying, okay, it's not just a bunch of symbols and numbers, it means something in ordinary everyday terms. And part of the objective of the course, in addition to just learning calculus, is to be able to look at equations and equations in calculus and to be able to understand what they mean in practical terms, and also in the context of real-world applications. So that's what we hope that you have gained from these lectures here.